I mean, if you drop your coffee cup, it shatters on the floor.
Right.
Yeah.
It doesn't put itself back together.
Exactly. Time just ticks forward. And the room you're sitting in, it stays completely still. But according to modern physics anyway, everything you just experienced is kind of a localized illusion.
Yeah, it really is.
Because everyday intuition gives us this deeply comforting set of rules to live by, you know. We just inherently feel that time flows identically for everyone, everywhere. We assume space is this fixed, empty stage. We think gravity is just a force pulling things down. But those impressions only work under incredibly limited conditions.
Right. Very, very specific local conditions.
Yeah. And the moment you introduce extreme speed or immense gravity, that comforting intuition just completely shatters. So today we are doing a deep dive into Sean Carroll's book, The Biggest Ideas in the Universe, Space, Time, and Motion. And we're going to explore exactly how physics dismantles that illusion.
And really, the primary tool we use to dismantle it is mathematics, which I think is crucial to establish right up front about how Carroll treats equations in this book. Because, you know, equations are not decorative symbols.
Right. They're not just there to look smart.
Exactly. They are not barriers designed to keep non-physicists out of the club. They are highly compressed statements about reality. So when our fuzzy human intuition fails us, equations step in to expose the hidden assumptions we didn't even realize we were making. They transform our everyday ideas into precise, testable knowledge.
Which is exactly how we're going to navigate this deep dive today. So over the next stretch of time, we're going to look at how physics builds this new picture of reality from the ground up. We'll start with basic models of motion, conservation laws, and why we actually need calculus to track change over time.
Yeah, the foundational stuff.
Right, the foundations. And from there, we'll see what happens when those classical models fail, diving into geometry, special relativity, and the realization that space-time can curve. We'll look at real-world tests of general relativity, push the math to its absolute extreme limit with black holes, and finally close out by discussing what scientific evidence actually means and the boundaries of our current knowledge.
So it's a progression, really, from the motion we can see with our own eyes all the way down to the fundamental structure of the universe that we just can't.
Okay, let's unpack this starting point. Because if we strip away the extremes and just look at classical motion, physics seems completely obsessed with finding what doesn't change. Why is that the foundation?
Well, because finding what remains invariant, what is conserved, is how you know your model of physical reality is actually coherent. I mean, think of a swinging pendulum. It's kind of the classic way to visualize conservation laws.
Okay, yeah, like a grandfather clock.
Right. As that pendulum swings down, it loses potential energy, which is the energy of its high position, but it gains kinetic energy, which is the energy of motion. And then on the upswing, it trades that kinetic energy backward for potential energy.
Right, but if I'm just watching a pendulum in my living room, it eventually slows down and stops. So my intuition tells me the energy just vanished.
Exactly. But it hasn't vanished. It's just transferring organized mechanical energy into less organized internal energy. So like heating up the surrounding air molecules through friction.
Oh, I see.
Yeah, we often make the mistake of thinking of energy as a physical substance, like water you can pour into a bucket. But energy isn't a substance. It is a calculated property of a system. The total energy across the entire closed system remains completely constant.
I really like that distinction. That it's a calculated property, not a physical substance. That requires a completely different way of tracking reality. Which I guess explains why Newton had to invent calculus just to describe how things move.
He absolutely had to, yeah.
Because, I mean, if I look at the dashboard of my car, I have the speedometer telling me my exact speed at this exact millisecond. But then I have the odometer telling me the total distance I've covered over the whole trip. They measure the same drive, but they are totally different concepts.
That is the perfect illustration of why physics absolutely requires calculus. Algebra just isn't equipped for it. Your speedometer is illustrating a derivative, meaning it captures an instantaneous local rate of change.
Like shrinking the time down to zero.
Exactly. It tells you your velocity at one exact moment by shrinking that interval of time down to almost zero. The odometer, on the other hand, illustrates an interval. It's the accumulated distance over a span of time.
Got it.
So calculus provides the discipline language to formally distinguish your position from your velocity and your velocity from your acceleration. Without those mathematical distinctions, you simply cannot build equations of motion.
But once you have those equations,
Yeah.
you enter this deeply deterministic world, right?
Mm.
Because if Newton's laws tell you exactly what happens next based on an object's current position and velocity, why is it that I can't get a perfectly accurate weather forecast for 3 weeks from now? The math is deterministic, so shouldn't the future be entirely predictable?
Well, this is where we have to separate deterministic laws from chaotic unpredictability, because the underlying equations governing the Earth's atmosphere are indeed deterministic. However, the weather is a classic chaotic system.
So even a tiny change messes it up.
In practice, yeah. If you have two nearly identical starting conditions, say a fraction of a degree difference in temperature over one specific city, those mathematical trajectories will just rapidly separate.
So the whole butterfly flapping its wings in Brazil causes a tornado in Texas idea
Yeah.
that actually ruins the math.
It ruins our ability to calculate the outcome practically, because our measurement resolution is finite. I mean, we can never know the initial conditions of the entire global atmosphere with infinite precision.
Right.
So perfect determinism exists as a mathematical ideal, not a guarantee of practical prediction.
Which brings us to a really good place to start using our accuracy framework for this deep dive.
Exactly. When we talk about Newtonian dynamics, we need to apply our first accuracy label, which is theoretical. And in our framework, theoretical does not mean a guess.
Right, in everyday language, theoretical means like, oh, I have a theory. But in physics, it's different.
Very different. It means a secure, incredibly accurate consequence of an established framework, provided you stay within its specific regime, which for Newton is low speeds, weak gravity, and macroscopic objects.
Okay, but the pendulum math and the Newton math all rely on this huge assumption that space is just an empty static container, like it's an inert stage where the physics happens. But Carroll completely destroys that assumption, doesn't he? He argues that space is a geometry all its own, even before gravity gets involved.
He does. But to understand that, we first have to separate the actual intrinsic geometry of space from the coordinates we use to map it.
Give me a terrestrial example for that. Are we talking about like latitude and longitude lines?
Yes, exactly. Think about standing exactly on the North Pole. What is your longitude?
Well, all the longitude lines converge right at the pole, so I don't really have one, or I guess I have every longitude simultaneously.
Yeah.
The map essentially breaks down.
It breaks down, and we call that a coordinate singularity. But notice, the physical ice beneath your feet at the North Pole is perfectly normal. The Earth itself isn't pinching into a sharp, infinite point.
Oh, right. The map is freaking out, but the territory is completely fine.
Precisely, and this is a major flaw in human intuition. We confuse our arbitrary labels for physical reality. Coordinates are just labels, they are not physical objects. A coordinate singularity belongs entirely to the map.
Okay, so if we accept that space has its own intrinsic geometry, and we throw out the Newtonian idea of a universal clock ticking away for everyone in the universe, what replaces it? How does that actually change our everyday reality?
It changes everything about how we understand causality and time. Special relativity replaces that universal clock, and it forces us to look at simultaneity completely differently.
How so?
Well, let's use a connective example. There are these fast, unstable particles called muons that are created when cosmic rays hit Earth's upper atmosphere. Now, they decay incredibly quickly. So if you use a clock sitting stationary on Earth, those muons absolutely should not survive long enough to reach the ground.
But they do reach the ground, right? We detect them constantly in laboratories.
They do. And they reach the ground because the elapsed proper time along their fast-moving path is fundamentally different from the time measured in Earth's stationary frame. From the muon's perspective, less time has actually ticked by.
See, this is the exact point where people throw their hands up and say, well, Einstein proved everything is relative. Your time is your time, my time is my time.
And we need to firmly correct that because it is a total misunderstanding of the physics. Relativity absolutely does not mean everything is relative. It actually means the exact opposite.
Wait, the opposite? How is it the opposite?
Because relativity is the search for what is absolute. It is about identifying what remains invariant while the surface appearances, like elapsed time or measured length, change for different observers.
So what is the absolute thing that everyone agrees on then?
The space-time interval. Special relativity uses what we call Minkowski spacetime. This unifies our three-dimensional space and our one-dimensional time into a single four-dimensional geometry.
Okay, you're going to have to unpack four-dimensional geometry for me. People always call it a four-dimensional loaf of bread, but what does that actually mean for my reality?
Right, the loaf of bread. So Think of the entire history of the universe, past, present, and future, as a solid block. That loaf of bread, different observers moving at different speeds will slice that block differently. So your slice of right now might be slightly angled compared to my slice of right now. We will disagree on how much space and how much time separates two events. But if we use the invariant equation to combine our space and time measurements, we will both calculate the exact same absolute space-time interval.
So the total distance across the slice is always the same. We're just measuring it with different rulers.
Exactly. And this absolute structure is enforced by geometric features called light cones.
Light cones?
Yeah, a light cone maps out the absolute boundary of what can possibly influence what, because nothing travels faster than light. Your world line is your unique path through this geometry, and your proper time is the time you physically experience along that world line.
And if we didn't have light cones enforcing this absolute speed limit, what happens?
Causality would collapse.
Oh, wow.
Yeah, effects could happen before their causes. You could receive a reply to a text message before you even sent it. The invariant rules of Minkowski spacetime are what keep reality logically coherent.
Okay, here's where it gets really interesting. We have this beautiful invariant four-dimensional space-time, but you haven't mentioned gravity yet, because every time I watch a science documentary, they explain gravity by showing a heavy bowling ball sitting on a stretchy rubber sheet, pulling all the little marbles down toward it. Is that what's happening to the loaf of bread?
Okay, we need to be very clear here. Do not treat those rubber sheet diagrams as literal physical reality.
Really? But it's everywhere.
It is, but it's a highly limited analogy that often causes more confusion than clarity.
Why is it confusing? It seems to make visual sense to me.
Because it relies on a heavy object pulling down into some higher, invisible extra dimension to stretch the sheet. But spacetime curvature doesn't require an embedding space outside of itself. The curvature is intrinsic.
Intrinsic curvature. Okay, I'm going to need a better analogy than the rubber sheet then.
Let's use the surface of the Earth again.
Mm.
If you draw a triangle on a flat piece of paper, the inside angles always add up to 180 degrees, right? But if you start at the North Pole, draw a straight line down to the equator, turn exactly 90 degrees, walk along the equator, and turn 90 degrees back to the pole, you've just drawn a triangle with three 90-degree angles.
Oh, wow. That's 270 degrees.
Exactly. You don't need to look at the Earth from outer space to know it's curved. You can measure the intrinsic curvature from right there on the surface just by seeing how the geometry behaves.
So how does gravity actually operate in that intrinsic geometry without just being a pulling force?
Through the equivalence principle. Imagine you are placed inside a small, windowless laboratory. Suddenly, it goes into free fall. Maybe it's dropped from a high-altitude balloon. While you are falling, if you let go of your pen, it just floats next to you.
Right, because we're both falling at the exact same rate.
Exactly. The equivalence principle says that local experiments in that freely falling lab look completely identical to experiments in an inertial frame far out in deep space, completely away from any gravitational mass.
But wait, what about the astronauts in the International Space Station? I mean, we see videos of them floating around eating floating water droplets. It looks like they're in an inertial frame where gravity has just vanished because they're in space.
This is one of the most persistent public misconceptions. Astronauts feel weightless not because gravity has disappeared in orbit. At the altitude of the ISS, Earth's gravitational pull is still roughly 90% as strong as it is on the surface.
Wait, really? 90%? So why are they floating?
Because the space station, the astronauts, and everything inside are in a state of continuous freefall.
Oh, I see.
Yeah, they are moving sideways so incredibly fast that as they fall toward Earth, the Earth's surface constantly curves away beneath them. In general relativity, gravity isn't a pulling force. Falling freely is simply an object following the straightest possible path, which we call a geodesic, through curved spacetime.
That is profoundly counterintuitive.
Yes.
I mean, it's beautiful math, but how do we prove the universe actually works that way?
We test it through exceptionally precise measurements. A major one is gravitational redshift. Because gravity is a manifestation of curved space-time, time itself flows differently depending on where you are in a gravitational field.
Wait, slow down. You're saying time ticks slower just because I'm closer to a massive object?
Yeah.
What is the actual mechanism there?
Think of a light wave traveling upward, away from a massive planet. As it climbs out of the gravity well, it loses energy. But light cannot slow down. It always travels at the speed of light.
Right.
So to lose energy, its frequency has to drop. Its wavelength stretches out, shifting toward the red end of the spectrum. And because the frequency of a light wave is essentially a clock, If the light's frequency changes, time itself is passing at a different rate relative to an observer further away. Clocks deeper in a gravitational potential physically tick slower.
I was reading that if we didn't account for this, the GPS on our phones would completely break down. Is
Yeah.
that just a slight rounding error, or does it actually impact my life?
Oh, it impacts your life every day. The GPS satellites your phone talks to are moving very fast relative to you, so special relativity says their clocks should tick slower. But they are also further away from Earth's mass, so general relativity says their clocks should tick faster.
So the two relativistic effects are just fighting each other.
Yes. And the general relativity effect is actually stronger. If engineers didn't program the satellites to compensate for this exact mathematical difference, your navigation app would drift by miles within a single day.
Wow. So relativity isn't just theory, it is literally powering my ability to find a coffee shop.
Exactly. So going back to our accuracy framework, we categorize both special and general relativity as theoretical. They are secure, profoundly tested consequences of an established framework. But general relativity also predicts phenomena that are directly observed.
Like gravitational waves.
Yes. When massive objects like two black holes spiral into each other and collide, they create literal ripples in the geometry of space-time. We test this using giant interferometers like LIGO. They fire lasers down perpendicular miles-long vacuum tubes.
Okay.
And when a gravitational wave passes through Earth, it physically stretches space in one direction and compresses it in the other.
By how much? Are we talking about a noticeable stretch?
We're talking about a distortion that is a fraction of the width of a single proton.
Good grief, that's small.
It is, but the interference pattern of those lasers allows us to directly measure it, so gravitational waves get the definitive label of observed.
Okay, since you brought up black holes, let's push this math to its absolute extreme limit. If gravity is just curved space-time, what happens when it curves so much that the equations break?
Well, when we discuss black holes, we have to carefully define our boundaries. People often conflate the event horizon and the singularity, but they are absolutely not the same thing.
So if I'm falling toward a black hole, my reality seems normal to me, but eventually I hit a boundary. That's the event horizon.
Yes. The event horizon is a causal boundary. Go back to our light cones we talked about. At the event horizon, the geometry of space-time is curved so severely that all future light cones tip entirely inward. There is literally no path through space-time that leads back out.
In the singularity.
The singularity is at the very center, and it is a completely different feature. The event horizon is just empty space, but the singularity is where the classical math of general relativity essentially blows up and produces infinities.
So let's apply our labels here. How do we categorize the event horizon versus the singularity?
We label astrophysical black holes, the actual massive objects out in the universe, as observed. We see their gravitational effects on surrounding stars. We've imaged the shadow of their event horizons, and we detect their collisions. But the classical singularity at the center, that remains entirely speculative.
Because we just don't know yet.
Right. It is an unresolved feature. We also have conclusions in physics that are model-dependent, meaning they rely on specific assumptions about the universe. But theories trying to explain the singularity with quantum gravity are currently just unverified, speculative proposals waiting for new physics.
So what does this all mean for us? We started this deep dive talking about Newton and swinging pendulums. If general relativity is a deeper, more accurate truth about curved space-time, does that mean all the Newtonian stuff we learned in school is just wrong?
Not at all. A more general theory does not make older physics useless. This introduces a vital concept called effective theories. Newtonian physics survives as a highly accurate approximation within its valid domain.
Meaning, if I'm building a bridge, I don't need to account for curved spacetime.
Exactly. If you are building a bridge or even calculating the trajectory of a rover going to Mars, Newtonian mechanics works beautifully. It is an effective theory for our macroscopic, low-speed, weak gravity scale. You only need the heavier machinery of general relativity when you approach the extremes. It's not about throwing away the old tools, it's about understanding exactly where those tools stop working.
I think that is the perfect takeaway. We began this journey with local, highly flawed intuition, the assumption that time is universal, space is an empty box, and gravity is a force pulling things down. And we've seen how mathematics replaces those fuzzy impressions with precise models. Models whose assumptions we can actually inspect, calculate, and, most importantly, test against reality.
And as listeners navigate any complex scientific claim, always demand that precision. Ask about the evidence status. Is the phenomenon directly observed through data? Is it theoretical, meaning it's a secure consequence of a well-tested framework? Is it model-dependent, relying on very specific parameters to work? Or is it speculative, a mathematical proposal waiting for verification? Demanding those distinctions is what separates science from science fiction.
Absolutely. Now, before we wrap up, we need to clarify that this deep dive is an independent Cosmora HQ book overview. It is not an official or complete audiobook of Sean Carroll's work.
We strongly encourage you to obtain Sean Carroll's published book, The Biggest Ideas in the Universe: Space, Time, and Motion. You can find it legally through your local library, a publisher, a bookseller, or any authorized digital or audio service. Seeing the full mathematical development for yourself is well worth your time.
Please make sure to subscribe, leave a comment with your thoughts, and share this deep dive with anyone else who loves looking under the hood of reality. We're going to leave you today with something to mull over, just a lingering thought to take with you. When intuition and an invariant equation disagree, what evidence should persuade us to change the way we imagine reality?